All right, so here's part one of two videos for section 11.1, two sample hypothesis testing for proportions. Again, I'm going to try to split it up probably somewhere in this little part here, probably right about here. Sorry, I'm going to split it up right at this second part where we relate a two sample hypothesis test with a confidence interval. So I'm going to split it up somewhere about right here. And then that way I can focus also on the minimum sample size, which is a lot of inverse operations stuff is what we got to do there. So let's get going here. So we're going to, in the first part here, we're going to talk about distinguish between independent and dependent sampling, and then also testing the hypotheses, regarding two proportions from independent samples is what we're going to go through and do. So when we're distinguishing between independent and dependent sampling, a sampling method is independent when an individual selected from one sample doesn't dictate which individual is to be in the second sample. A sampling method is dependent when an individual selected to be in one sample is used to determine the individual in the second sample. Dependent samples are often referred to as matched pair samples. It is possible for an individual to be matched against himself or herself. We're going to see that in a couple examples in this thing when in medical trials. Sometimes it's better to if we're trying to make a decision about whether a certain drug helps a certain condition. It's better to use if you can run the same person through the experiment with the two different types of treatments, then that's kind of like a matched pair. Or I've used the analogy. My brother and I are about a year apart in age. We have the same genetics, and so if we were trying to do to see if a certain blood pressure medicine, let's say, was effective for a condition and so forth, then using my brother and I, we kind of take away all the different type of biases out there, and then we just need to be randomly assigned to make sure we keep the trial process from being biased. We randomly assign my brother and I to having either the placebo or the experimental medicine, and then that way they can make a decision: does this help? Does this medicine help? Whatever it may be, lowering blood pressure or whatever. As we go through, here's the first one. It says, among competing acne medications, does one perform better than another? To answer this question, researchers applied medication A to one part of the subject's face and medication B to a different part of the subject's face to determine the proportion of the subjects whose acne cleared up for each medication. The part of the face that had received medication A was randomly determined. And so this is an example of a dependent sample. And more specifically, it's an example of that matched pairs because they were putting, as I go to find a pen that works a little bit better, this is an example of a dependent sample. Sorry, my apologies. So the dependent sample, it is a matched pair because we had the same person. They did both treatments. They had medication A and medication B. So they ended up being, both parts. So let's see what's causing us to have some issues here. So this would be a dependent. And more specifically, it would be a matched pairs. Scenario 2 here says, do individuals who make fast food purchases with a credit card tend to spend more than those who pay the cash? To answer this question, a marketing manager randomly selects 30 credit card receipts and 30 cash receipts to determine if the credit card receipts have a significantly higher dollar amount on average. This would be independent. This would be independent sampling. And again, the reason was because the credit card and the cash receipts were totally different set of separate random samples. One's not going to dictate the other because one, it probably didn't have the same people involved in the process. So it was more it was more in line with the independent. Joliet Junior College decided to implement a course redesign of developmental mathematics programs. Students either enrolled in a traditional lecture format course or a lab-based format in which lectures and homework are done using videos and course management system, which is called MyMathLab. There were 1,200 students enrolled in the traditional lecture format and 300 were enrolled in the lab-based format. Once the course ended, the research determined whether the student passed the course with an A, B, or C, or not. The goal of the study was to determine whether the proportion of students who passed the lab-based format exceeded that of a lecture format. And again, this would be an example of an independent, is what this would be. Independent sampling. Next one, are products purchased on Amazon less expensive than those purchased on Walmart? To answer this question, researchers randomly identified 20 products sold at both stores and determined the selling price at Amazon and online Walmart stores to determine if there was significant difference in the price of goods. And again, this would be an example of dependent. And the reason why it was dependent is because they did the first selection of the products at Amazon, and then they did the exact same products at Walmart. So they used they used the same products in both situations to compare the difference. So this is more of a dependent sampling. All right, so our hypothesis test regarding the difference between two population proportions. When we go to perform a hypothesis test regarding two population proportions, the samplings are independently obtained using simple random sampling or some randomized experiment with two levels of treatment, which means having like a placebo and having the actual treatment itself. When we go to do the normal and large count condition, you got to take each sample size, multiply it by its probability, and one minus its probability got to be greater than or equal to 10. Then when we look for the independence piece as well, is for each sample is 0.05 times the population greater than the sample size that we did. And again, this ensures the independence necessary for the binomial experiments. Again, we still have, when we write our testing, we still have our alternative and null hypothesis. The only differences here is we're going to have saying that P1 equals P2 in our null hypothesis. Now, you could say, if you wanted to, you could say P1 minus P2 equals 0. There is no difference between the two. Again, we got that by, well, if we start off with P1 equals P2, if we subtract P2 across, then that's how we get the P1 minus P2. So you could have in the null hypothesis that the difference between the two is 0. If you want to write them as P1 equals P2, that's perfectly okay. Same thing with alternative hypothesis. We got to make sure, what are we doing, a left tail, right tail, or two tail? That dictates which type of inequality symbol we need to use. If we decide to go with the calculating the Z statistic by hand and going to the table to figure out, where is, what is the p-value, then we need to do what we call, it's called pool or combine the data. And we only pool or combine the data when we're dealing with proportions. So that's one thing you want to make note. We only pool or combine when we're dealing with proportions. Proportions. And again, on the TI-84, they actually give us that option, and I'm going to show you where that is. This is where basically when we're doing a pooled or combine the data, we are combining the p-hats. So we take the successes for each one, for each sample, add them together over the total number in each sample added together. And then we go ahead, in order to figure out the Z statistic, we would find the difference between the two p-hats. And then on the bottom, in the standard error part, it'd be the square root of, and instead of using the p-hats here, we would use the combined p-hat is what we do. The PC hat is what we would use over each top of the sample sizes. Using the TI-84, we can go over into stats, over to test, and we're going to do a two-prop Z test. Enter information for X1, X2, N1, N2, choose the appropriate inequality symbol. Again, this is where we do pull our data, is what we do here. We go ahead and do our get our p-value and z-statistic. They're listed on that screen. Then we make our decision. If the p-value is less than the alpha, we reject the null hypothesis. If it's greater, we fail to reject. Again, we'll do some of those here in a moment. So they asked us to go through in each of these. They tell us the alpha is 5%, so that's what we're comparing it to. They want us to determine the null and alternative hypothesis. They want us to get the test statistic, the critical value, and the p-value. And so remember, the critical value when we're dealing with proportions is through the inverse norm, is usually where we're grabbing that one from. It's from inverse norm. Unless you use that table A, is what we're using there. So there, the inverse norm is where we get that critical value. So let's go ahead and start our null and our null and alternative hypothesis. So for the null hypothesis, we are going to say that P1 is equal to P2. The two proportions are equal to each other. So my alternative hypothesis, they tell us right here, P1 is greater than P2. Now, we don't have a context of the problem, so we don't know what the P1 and P2 stands for, the proportion of what. So now we want us to go through and find the test statistic. Again, you can do it by hand. I'm going to use the calculator feature, and I'm going to do a 2-prop z-test. And I'm gonna put this information in there, and so I'm gonna go x1 is equal to 368. N sub 1 is equal to 541. X sub 2 is equal to 351. N sub 2 is equal to 593. And then the next thing we got to do is we need to choose that we are greater than. P1 is greater than the P2. So with that in mind, let's split our screen, get a TI-84 calculator up here. And let's see, there we go. So clear that out of there. All right, so with that in mind, we're gonna go stat over to test. Two prop z-test is option number 6. And now I go ahead and start typing that in. 368, 541, 351, 593. And we're doing that we are greater than P2, so that's the last one. Go down to calculate, and I hit enter. And then now, as I look at labeling, okay, what's my z-statistic? So the answer to that fraction, our z-statistic, is 3.0838. And again, round to whatever decimal place they want you to. Our p-value is 0.00102. And that's it. They just wanted us to grab those things there. They tell us to assume that the samples were independently using some simple random sample, so we were fine on our condition there for independent. Didn't have to worry about. We could go through and figure out the large count normal condition, but we're okay that. So now we're supposed to compare that thing there to 0.05. So as I compare it to 0.05, I realize that is less than 0.05. So in that case, we would say we would reject the null hypothesis. There is convincing evidence. There is convincing evidence supporting whatever was stated in the alternate hypothesis, that the proportion in 1 is greater than 2. There's supporting evidence in that. All right, next one. Again, same thing. We're the same kind of setup here. We're doing a greater than again. So again, as I write my null hypothesis, in the null, we're saying that the two things are equal to each other. In the alternative hypothesis, they want us to do P1 is greater than P2. And then I'm going to type all this data into my 2-prop z-test to get all the other information. So stat test option 6, and we're going to go 109, 475, 78, 325, and we're again using the same. So we're going to just go ahead and hit enter. And this one has me, let's see, it has the z statistic as negative 0.3455. I have a p-value my p-value is 0.6351, and as we look at comparing 0.6351 to 0.05, that is actually greater than. So in this case, we failed to reject the null hypothesis. There is not convincing evidence. There is not evidence to support the claim in the alternative hypothesis that P1 is greater than P2. All right, again, next one here. Here's my alternative hypothesis. Again, the null hypothesis, the H sub O, P1 equals P2. The alternative hypothesis, P1 is not equal to P2, so there is no difference between the two. Let's go ahead and put that stuff in there. So stat to test, go down to 2-prop z, whoops, sorry. And then let's put those in there, 28, 254, 36, 301. Choose the not equal to symbol, go down to calculate. And here I have a z statistic. The z statistic of negative 0.3441 and a p-value apologies with my pen. My p-value is 0.7307. So that is greater than 0.05, so we would fail to reject. Okay. All right, so now let's skip down here and let's go into like a more of a word problem situation and kind of go through the process. I'm going to move the screen over to give us a little bit more. So the drug Prevnar is a vaccine meant to prevent certain types of bacterial meningitis, typically administered to infants around 2 months. In randomized double-blind clinical trials of Prevnar, infants were randomly divided into 2 groups. Subjects in Group 1 received Prevnar, while subjects in Group 2 received a control vaccine. After the first dose, 107 of the 710 subjects in the experimental group, Group 1, experienced fever as a side effect. After the first dose, 67 of 611 of subjects in the control group experienced fever as a side effect. Does the evidence suggest a higher proportion of subjects in Group 1 experience fever as a side effect than subjects in Group 2? And we're doing it at alpha of 5%. So as we look at our null hypothesis, we're just going to go Group 1 and Group 2. So is the proportion in Group 1, is it equal? That's what we're testing. Are they equal? The alternative hypothesis, they stated here, does the evidence suggest a higher proportion of subjects in Group 1? So we're doing here, is Group 1's proportion greater than 2? So, and then again, in a true writing it out, we would actually define what P1 and P2 means in the context of this problem, where P1 is the proportion of infants that got fever as a side effect from group 1 and so forth for same thing for P2. Now we're going to go ahead and do our test. So we're going to do our 2-prop z-test. And we're going to be putting in there that x1 is 107, n1 is 710, x2 is 67, n2 is equal to 611, and we are doing greater than P2. So let's grab our calculator, put that in there. And stat over to test, option number 6. 107. Remember, you can always pause this if I'm going fast. 710, 67, whoops, and 611. I realized that it didn't get my 0. There we go. And we are doing greater than. It looks good there, double checking. Hit enter. We have a Z statistic of 2.19956, and then my p-value is 0.01392. So then I would go through and compare that to a 5% alpha. So up here I'm going to say 0.01392 is less than 0.05. So since that's the case, so since 0.01392 is less than 0.05, we reject the null hypothesis. There is convincing evidence to support the claim excuse me, to support the claim that there is a higher proportion, I'm going for this part right here, higher proportion of subjects in group 1 who experienced fever as a side effect. Then group 2. All right, follow-up question on the Prevnar. Prevnar in a random double-blind clinical trial. Double-blind, if I don't remember if I mentioned it before, that basically means that the patient and the person doing the experiment have no idea who's being assigned to it, who's getting what, who's getting the normal vaccine, who the people are, and so forth, and who's getting the new Prevnar. That's what double-blind means. Not only do the participants don't know, but also the people conducting it have no idea, who's getting what as they randomly assigned. So they asked us they gave us another situation. Sorry, my pen, there we go. I got the numbers back in here. So they went through and did a second dose, got some information. The next thing was they experienced drowsiness as a side effect. Does the evidence suggest a lower proportion of group 1 experienced drowsiness as a side effect compared to 0.2? So that lower proportion in 1 tells me that my alternative hypothesis, P1 is less than P2. Now, our null hypothesis is still P1 equals P2. And then here's all my information for my process, x1, n1, x2, n2. So let me go ahead and get my calculator, just try to speed the video up here. So stat over test, option 6, 137 out of 452, 31 out of 99, and we said less than, so that middle one. And then go down to calculate, and I see here that I have a z statistic of negative 0.1964 and a p-value of 0.42214. So now if you decided to use the classical method and got the fraction and got your z statistic, and then we went around and did a normal CDF with the information, we would find out that actually that the z statistic is not in the shaded zone of the normal distribution of what we would shade for the reject and do not reject. So here again, as we compare it, since 0.42214 is greater than 0.05, we reject the null hypothesis. There is, sorry, totally blanked. My apologies. We fail to reject. We fail to reject. We do not reject. We do not reject. That's what fail to reject means. We do not reject the H sub O. There is not convincing evidence to support the claim that the proportion of subjects in group 1 who experienced drowsiness as a side effect is less than the proportion in group 2. Okay. So this will be the last one. Then we'll stop and we'll pick it up in a part 2 video for the remaining stuff. Abstaining from alcohol. In October 1947, the Gallup organization surveyed 1,100 adult Americans and asked, "Are you a total abstainer from, or do you on occasional consume alcoholic beverages?" Of the 1,100 students surveyed, 407 indicated they were total abstainers. In a recent survey, the same question was asked to 1,100 Americans, and 333 indicated they were total abstainers. Has the proportion of adults who totally abstained from alcohol changed? Use the 5% level. So, has it changed? Now, when they look at it, has it changed? They didn't indicate it went down or it increased, so that would then be a not equal to, is what that's an indicator. So, in our alternative hypothesis, our P1 is not equal to the P2. Again, null hypothesis, they're equal. And so now I'm ready for my test. So I'm going to go stat over here, just trying to go through this last one quickly. So the first survey, that would be the P1. So 407 and 1100. The second survey would be the 333 and 1100. And then we're doing the not equal to. So my Z statistic on this one was 3.33926, and then my p-value is 8.40118, but then it says e to the -4, so that's really 0.00084. So now I do my little wrap up here. Since 0.00084 is less than 0.05, we reject the null hypothesis. There is convincing evidence to support the claim. That the proportion of adult Americans who totally abstain from alcohol has changed. Remember, they didn't say it increased or decreased, they said it has changed. So we have evidence that it has changed because our p-value is less than the alpha.